we can use the Laplace transform to transform circuits into the S domain. Recall that the voltage of an inductor is equal to L di dt, where I is the current through the inductor. If we perform a Laplace transform of this equation, we will get capital V of S is equal to L, and then this is I prime, so we can use the expression SIL of S minus IL at the initial time 0. This lends to an interesting transformation. If V of t is across this inductor, then we can rewrite this as V of S, where V of S is the sum of two terms. First, there is a quote-unquote inductor, which we will call LS, because LS times I is V. That follows Ohm's law. So this is an ohmic thing. Secondly, we have this term L times negative IL. Now this is actually a constant because IL at 0 is a constant and L is a constant. So we can actually write a voltage source which is in the opposite direction of voltage V of S, which has the value LIL at 0. And we now have a transform of the inductor. I will now proceed to give you some pictures from the book that look much prettier than my own diagrams. An inductor can be transformed into either an inductor plus a voltage source that has this form, or an inductor and a parallel current source which has this form. Meanwhile, a capacitor can be transformed into this form or this form. Finally, if you have a voltage source which turns on at time equals 0, you can represent that as whatever V value it has times the function U of t. This is the unit step function which turns on when time equals 0. This simply transforms into a voltage source which looks like V over S, because U of t turns into 1 over S according to our Laplace transform pair, when U of t starts at 0. If it doesn't start at 0, things get way more complicated, but thankfully in circuits, you don't have to deal with that. Although if you're in ordinary differential equations, you totally have to deal with that. But I'm not going to teach that in this video. Check out my TA hours. This way, we can represent voltage sources and current sources in the Laplace transform form. By the way, I believe that if there's not a unit step function, you should still treat there as basically being a unit step function. If you see a voltage source or a current source in a circuit, just always turn it into V over S or I over S if it is either V or V times U of t. Just things to know. As an example, let's try and solve this circuit. This 25 e to the negative t U of t voltage source does have a function in front of it, but if there's a function multiplied by the unit step function where the unit step function is at 0, then we can simply transform this to be, and so let's write our voltage source here, the transform of this bit. We can ignore this bit, we can just focus on this bit. So this is 25 e to the negative t, which gives us 25 over S plus 1. Now the inductor here we can transform either using this form or this form. I think that this form is going to be best. We do need to figure out what I at 0 is originally, but if you notice, both this current source and this voltage source turn on at time equals 0, so the initial current is simply 0. So that means we don't even have a voltage source to speak of. This thing is just that. So we're just left with SL. So our inductor we will draw as 1 times S, or just S. Now, knowing that our capacitor also has 0 volts across it at time equals 0, I suspect we shall use this form of the transformation of a capacitor and just poof away the voltage source because V is 0 is 0. So we're left with 1 over SC for our capacitor. So let me write that down. That's 1 over 2S. 1 over 2S. The resistor is 4, and the current source is going to be 4.5 over S because mu of t directly turns into 1 over S. It remains to analyze this circuit and determine what the voltage across this capacitor is. To do so, I'm actually going to perform a source transform. Don't we love source transforms? Remember those? The left side of the circuit remains the same, while this current source and resistor in parallel become a 4 ohm resistor in series with a voltage source, which is 4 times this. 4.5 times 4 is 18, so we have here 18 over S as a voltage source. And now we can use a cool mesh analysis. I'll write my meshes as the following: I1 and I2. Then I can write KVL. KVL for loop 1 is 25 over s plus 1, the voltage source, minus I1s, minus I1 plus I2 times 1 over 2s. I'll just divide by 2s here, and that'll equal 0. Actually, no, stop. I'm going to use a nodal analysis. Why am I going to use a nodal analysis? Because I want to get the voltage over this capacitor directly, and that's just going to be V if we use a node. So, time for nodal analysis instead. We'll draw 3 currents, I1, I2, and I3, and we can now use KCL at this node. I1 plus I2 equals I3, so we have that I1 is equal to the voltage source minus V over S. So 25 over S plus 1 minus V over S, and then I2 is going to be similarly 18 over S minus V over 4, and that's going to be equal to V minus 0, because this is our ground, or so V all over 1 over 2S. And our goal now is to solve for V and inverse Laplace transform it. And it's all just algebra from here. Ha 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 ha. We'll do some simplifications. This nested fraction can be turned into 2 fractions by just putting s in the denominator of both these guys. So we have 25 over s plus 1 minus v over s. Then over here we'll do the same thing. We'll stick 4 in both to get plus 18 over 4s minus v over 4. And finally here we have, this is just 2sv. To get rid of the 4 s's in the denominator for now, I'm going to multiply everything in the world by 4s. Remember, I'm trying to solve for v. I just do not like that there's weird denominators of v, so I'm multiplying by 4s to get rid of everything. So if I multiply by 4s, we get here 100 over s plus 1 minus 4v plus 18 minus sv is equal to 8s squared v. If we solve for v on the right side by combining like terms, we have on the left side just 100 over s plus 1 plus 18, on the right side 8s squared plus s plus 4 over v. Now I'm going to solve for v by dividing by all of this, but first I want to turn this left side here into a nicer single fraction. So we'll multiply 18 by s plus 1 to get 100 plus 18 s plus 1 all over s plus 1 is equal to blah, 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 blah. And so we can simply finally write that v is equal to 18s plus 118 in the numerator over s plus 1 times 8s plus s plus, and then let me see what this is, plus 4. So now we have a expression for v that we simply need to inverse Laplace transform. Simply, we are so far away from done. I'm going to factor 8 out of this fraction to give us 1/8 times 18s plus 118 all over s plus 1 times s squared plus s over 8 plus 1/2. Then I can complete the square in the denominator here. This completion of the square gets a fair bit hairy. But in the numerator, we have 18 over 8 and 118 over 8, which gives us a grand total of 2.25s plus 14.75 over s plus 1 and this monstrosity. We can then perform partial fractions to this. This is equal to a over s plus 1. Really nice. And then on the right, we get b times s plus 1 over 16 plus c over blah, 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 blah. Anyway, it's not great. Let's multiply everything by the denominators to get this whole wonderful mess. 2.25s plus 14.75 on the left, and then a times all of this, plus b s plus 116 plus c times s plus 1. I'm going to multiply some stuff out. I mean, this returns to our original. Actually, we're just going to plug in clever s's. If I plug in s equals -1, this whole thing disappears. The left side here becomes 12.25, and then what's in here becomes, well, by reasons, 352 over 256. And if we solve for a, we get 98 over 11. How exciting. Honestly, you can probably just be using numbers, but I think that... Let's plug in -1/16. The -1 over 16 cancels out the b, and to an extent this part, so we get 127 over 256a plus 15 over 16c. The b goes away, so -1/16. Anyway, 15 over 16c, take my word for it. More mess. I am continuing to solve for a and c. I just plugged in some stuff. Anyway, c is basically equal to 10.97, so we'll just stick with that for now. In order to quickly solve for a, I'm just going to collect all the s squared terms in this entire situation. And we know that the s squared term here is simply as squared. And the s squared term here is just going to be bs squared. And we know that there's no constant in front of s squared on the left side here, so that's just equal to 0. So we now know that a is equal to negative b. b is therefore equal to negative 98 over 11. From the original format here, then, we've got our 98 over 11 times 1 over s plus 1, minus 98 over 11 of all this mess, and then 127 over 256 is equal to 11.27 over 16 squared. That's also 0.704, so I'll replace every instance of 127 over 256 with 0.704 squared, and finally we can inverse Laplace transform this into 8.9 e to the negative t minus 8.9 e to the negative t over 16 cosine 0.704t plus 15.58 e to the negative t over 16 sine 0.704t. Now we can do a quick check to see if this is right by plugging in t equals 0 and t equals infinity and seeing what we get. At t equals 0, this is 8.9 and this is negative 8.9, so this just goes to 0 because it's 1. But at t equals 0, this goes to 0. So we have v is 0, and we remember in the original form of the circuit, the initial voltage is supposed to be 0. Now at time equals infinity, let's think about what's going on in this circuit. This voltage source should be gone because it will have decayed to 0, and this inductor will act as a short. So the current will go straight through the inductor, and there will be 0 voltage drop across the inductor, and therefore 0 voltage drop across the capacitor. So the final voltage should be 0. Let's check if that's also true. At time equals infinity, all of these exponential decay functions will have become 0, so the whole thing will be 0, so this seems about right. And in good news, it turns out that this is exactly the right answer according to the book, although the book expresses it differently. I'm sorry for doing such a complicated example, but to be fair, most of the complication was in the math, and there are probably easier examples out there. Maybe I'll have P-Stan make a video about one of those easier ones for you. But I am done. We have successfully solved for the voltage in this capacitor without having to solve a differential equation that we create from scratch, which I think is a positive thing. Anyway, I promise to have nicer examples for the class times, but thank you for listening. Goodbye.